So now let's talk about the end behavior model. So the end behavior model of a function, of a rational function, I should say, f of x, which means that it's basically a function over a function, so like x squared plus 3 over x cubed plus 1. It doesn't really matter. And it's saying take the highest power on the top and divide it by the highest power on the bottom. So the end behavior model of f of x in this case would be x squared over x cubed, which just simplifies to 1 over x. You ignore these constants, and here's a little interesting fact about end behavior models. The limit as x approaches infinity, or negative infinity, I'm not going to write it because I run out of space, of f of x equals the limit as x approaches infinity of 1 over x. And that makes this so much simpler. You don't have to, go crazy plugging in values and seeing what this approaches, if it's going to infinity, if it's going to 0, and if you remember from a little bit ago, that does in fact equal 0. So the limit as x approaches infinity of both f of x and its end behavior model are the same for infinite limits. And that comes in it comes in real handy when we look at more complex examples. For example, I'm just gonna make one up right here. Let's say g of x equals 100,000 plus 4x cubed plus 8x squared divided by log base 18 of 40,000 plus 24x plus 35x cubed. Now, if we hadn't talked about end behavior models, this would be a monstrosity. You'd probably be, I would be freaking out about this. I wouldn't know what to do if I didn't have an end behavior model. So what we're going to do instead is just make this entire mess just go away. We're just going to take the highest power on the top, 4x cubed, and divide it by the highest power on the bottom, 35x cubed. And when I say highest power, I also mean the coefficient with the power, just to specify now. So that's 4x cubed over 35x cubed. If we factor out the x cubes, we get 4 over 35. And then we have the limit as x approaches infinity of 4 over 35, which is a constant, meaning that the limit equals 4 over 35. And that's so much simpler than what the question gave us. The question gave us this whole mess here. So why does this work? Why does the end behavior model work for limits involving infinity, or negative infinity, and sort of any infinite value? Infinity, negative infinity. Let's take a look at this function. F of x equals x squared minus 1 over x squared plus 1. So if we use end behavior models, we'd get the limit as x approaches infinity of x squared over x squared, which is just 1, and thus the limit would equal 1. But let's try and figure out why the end behavior model works. And so let's think about this for a bit. Let's say we don't know end behavior models, and we just want to keep plugging this in larger and larger values until we get an approximate answer. So let's try first 10. So this should be f of 10, and let me just write this up here so that we know why we're doing this. So limit as x approaches infinity f of x, we're just going to be plugging in larger and larger values. So f of 10 equals 10 squared minus 1 over 10 squared plus 1, which is 99 over 100. Very close to 1, but not exactly 1. Let's try f of 100. F of 100 is 100 squared minus 1 over 100 squared plus 1, and 100 squared is 10,000. 10,000 minus 1 is 9,999. Sorry, this up here is 101. Sorry about that. And then this right here is 10,000 plus 1, so 10,001. And that's even closer to 0. I'm sorry, even closer to 1 than what this top one was. And if we continue this, we're going to find that it gets infinitely close to 1. Because as the larger powers get bigger and bigger, these smaller numbers, in this case they're constants, become less and less impactful on what the outcomes of these two are. And this is true for any function. So let's say we have f of x equals x cubed plus 40x squared over 4x cubed plus 80x 3/2. So solving this without the end behavior model would be terrible. But let's think about this. X to the cube and 4x cubed, if we're getting infinitely large values, these guys, they're going to be overproducing these smaller constants, x squared and x to the 3/2. These cube terms are going to be infinitely more large than these will ever be as we get larger and larger values, because these will always be growing at a faster rate. And as long as we're inputting infinitely large values, they will be infinitely larger than these could ever impact on them. It'll eventually become so small because we're using infinite values. The gap will become so big that these are like so small compared to these terms. Like if we did f of a googol, which is I believe 10 to the 100th power, these are going to be so much larger than these terms. It doesn't matter what the coefficient is or what the power is. As long as it's less than the power of this x term, they're going to be less. They're going to always be less in the long-term run than these guys. And so they will be so unimpactful on what this end result's going to be. And that's why the end behavior model works no matter what, because we're always going to have those powers that matter the most towards the limit. We're always going to have those constant. We're going to have those with us. Whereas we're going to drop the less important terms, and then we can just simplify and then solve the limits so much easier. And so that's pretty much all you need to know about end behavior models for infinite limits.